Welcome to Savoir Labs. I'm Jamie Goodyear. A little while back, we installed a Nvidia RTX 1000 graphics card into our Dell R250 server. Let's tune Ollama to get the most parallel processing out of it. Up next. Okay, let's get into how we tune an Ollama server. Before we do that, I want to get onto the terminal and show you what parallel processing means in this case. So I have tmux set up with 3 terminal connections to my Ollama server. I've lined up a request for Ollama to process the Mistral model with the prompt, why is the sky blue, why is the sea blue, and why is the world round? If we were to do this sequentially, we'd expect it to take so many seconds for each one of these terminals to complete, and the total runtime would be the summation of those. If we're doing this in parallel, however, we'll see all 3 of these terminals executing and getting a result back at the same time. Our question is going to be, how many parallel prompts can we do at the same time? So let's take a look at this simple process here, and then we'll start scripting this out. Okay, that was pretty quick to get all 3 back, but what happens is we increase the number of requests and set up Ollama to process a lot more. Let's discuss what Ollama provides us for tuning parameters. Each one of these tuning parameters are presented as an environmental variable, so when we want to use these, we're going to have to stop Ollama and then restart it to load these into the running process. The first level of concurrency parallelism that is supported is the number of running models. Now, our card has 8 gigabytes of space, so in theory, we could run a couple of small models along with their context. We are going to do just one model. We want to be able to say, for one model, how much parallelism can we get for that, instead of just saying how many models and how many permutations of that can we get. You can set the number of parallel requests. Now, Ollama will start off with either 1 or 4 as the default values. The way it does is that if you do not have a lot of memory, it will set you down to 1. If you have more abundant memory, it'll set you to 4. This is usable, user settable. So we're going to be tweaking this value and running a script to find out what happens as we do that. We can also set up the number of messages that will get queued. Now, this queue is a little bit special in that it is all these requests come into Ollama, they'll go down to the queue, and as it gets processed, we'll read from that queue. Any additional requests coming in during that period will immediately just get rejected because we're busy. But if there's space, it will come in. This is something that developers can see as being an opportunity to optimize around, but we're not going to focus on that for our testing. We're going to keep that queue reasonable size so we can just get a lot of messages in there and see how fast we can process that backlog. And we can also set the context length. So this is the size of the context that the model is going to be running. Obviously, you can do this via the API, but you can also do it by environment setting. We're going to keep everything consistent here because we're going to be testing across models, and we're going to keep it at just over 2,000 tokens. Keep in mind that when you want to test for your own applications, you're going to want to test a little bit larger towards the size of the context you're going to be using. So the design of our script, and you'll find a link in the show notes down below to what we're using, effectively sets up a client that's going to send 128 requests very quickly into Ollama. Ollama will queue those up such that now the service can start reading those. For clarity, what I'm showing here for Ollama is that there is the base service that is running, and then there is what I'm going to call the memory space. This is effectively the space that we are running our model and all of our contexts, i.e. our video card RAM, where we want things to be running, because that's going to be the fastest solution for us. The biggest amount of your memory is going to be for your model. So we're going to be loading one model in each one of our tests, and then the number of contexts. So you want to have 1 request being processed at a time, all the way up to, in our case, we're going to go up to 16. In our testing, what we have is the Nvidia RTX 1000 88 8GB of RAM. We're going to test Mistral, Llama, and deepseek R1 in the 7B format. And we're also going to do deepseek as the 1.5B. We are going to tweak the loaded models to 1 to make sure we only have 1 model in the machine at a time. We're going to go from parallel setting of 1 up to 16, and we're going to do this groups of 1, 2, 4, 8, 16. We're going to keep the maximum queue at 512 for all of our tests, and a context length static at 2,000 tokens. And we're sending 128 identical prompt requests to Ollama, so that way they are somewhat equal amounts of work. Keeping in mind, between every one of these tests, we had to stop and restart our Ollama. So let's have a look at our results, starting with Mistral. This was a 7B model, and let's start with the bottom graph here. What this is showing is the number of seconds it took to process the entire collection of 128 requests. So when we have one parallel request being processed at a time, it was taking just shy of 600 seconds. That's about coming on 10 minutes there for it to process. As we increase the number of parallel requests that could be processed, we actually see that there is a sweet spot in where we get the most bang for buck performance. Because if we go all the way up to 16 parallel requests, we actually see it starting to slow down. There is context overhead, context switching, all these things we can assume under the hood are happening. So there is a point at which this card is becoming optimal. On the right side of the screen, we also see the memory pressure at each one of the parallel requests. We can see at 1, we just have the load of the context plus the model being in memory. When we get all the way up to 16, we can see the effect of having all these additional contexts. I also want to make sure we're very well aware that we are not using the full size of a possible context for this particular model. We're only using the beginning part of it. So if you want to have more context length, you're going to need to have a little bit more headroom. But for Mistral, what we can say is that at around 4 parallel processes, we are kind of getting to that sweet spot where you're getting quite good performance, and we still have some overhead space to allow for context. What's important to note here, though, is that's still taking about 200 seconds. So if I was using this in a production system, I'd be looking at more of a batching system, not something that tries to be responsive to end users. When we tested the llama model, also 7B, we see a little bit of a different behavior here. As we increase the number of processors, we actually saw that the throughput was slightly improving all the way through. However, when we look at the memory pressure, we see that we are paying quite a heavy cost. Again, it comes out that there's a sweet spot. 4 parallel processes gives us relatively good throughput for this particular model and plenty of additional space for our context. I will note, though, that this is at 400 seconds approximately to process all 128 requests, so it is not, again, something I want to be using other than a batching request. Now, let's move on to deepseek in the 7B format. This one has that graph where we see the more parallel processing we have, we actually get diminishing returns. What's more concerning here is actually it takes quite some time, according to our testing, for all of this to run. I actually had to run this a couple of times just sequentially, just to verify that these times weren't completely out to lunch, because it is quite a bit of time for this card to run it. But what we do see memory-wise is that we still have quite a bit of space here available, so that's good. But again, I would only be using this model in the sense that I need to have how it performs for the application I'm writing. It definitely is a pretty slow one for getting maximum throughput. Then we put in the deepseek R1 1.5B model. This one is incredibly quick, all the way down to 16 parallel requests. We see we have plenty of memory left for its relatively large context size it can handle. And yeah, this one is very, very sippy. That being said, it's a very small model, so if I was going to be using this, I'd be using it for something, say, like summation. That being said, it could be used for something a little bit more quick reply if we know we don't have a lot of parallel requests coming in at all the time. So let's step back and take a look at the overall picture here. Between the 7B models, it kind of becomes clear that we're looking at between Mistral and Llama for systems that are going to be relatively quick to be able to process a large number of requests, with the 1.5 being the absolute speed king on this particular card, and then the DeepSeek 7B model is being quite slow compared to any of the other ones. So what does this mean for developers trying to use this card and Ollama to do local reference inferencing? Well, what it's telling me is that you're going to have to pick your model very carefully, one that has the accuracy towards the job that you're doing. And now we're going to want to start tuning it for this card. We can use what I provide here as a baseline to start your testing. But what you're going to want to do is set the number of parallel requests you can handle, and keep in mind that the overhead you're going to have is the number of contexts and their size that you're adding in plus the model. So smaller models, you're going to be having more space for those contexts. Keep in mind every model has a different maximum size to its context. You're going to want to set the context length to something reasonable. For all my tests, I kept it at a relatively small size of 2K. If you're doing this for an application that requires much larger, i.e. you're passing in lots of, say, text and you want to get a summation of hundreds of pages, yeah, you're going to need to set that up larger and validate that you can handle multiple of those concurrently if that's not an outlier size for you. The queue size, this is something really important to keep in mind. It will reject brand new requests if it is full and busy. You can set this to be a very large number so that you don't get too many rejections. The challenge I have with this is that when I would send in my 128 requests, those requests, and you can see in the logs, is that they all pretty much start timing at the beginning when they all start up. And for those last ones, if it took several minutes, that request has been running now for like 3, 4, 5 minutes. If you have an application that's trying to expect this to be like a RESTful application that you post and get a response, 4 or 5 minutes is going to be way too long. So keep in mind how this works, and somewhat smaller queue might actually be beneficial, because if you're seeing that it is full, you're not going to have 100 jobs just sitting there that won't be seen for another 2 or 3 minutes. You might actually want to take advantage of that behavior. Now, with all of that being said, I want to thank you for joining us on this video. Please leave any comments you have down in the notes below. Please like and subscribe, and see you on the next video. Have a great day. Cheers.